Hey, so far in this class, the basic idea has been I give you a function, you take its derivative. Well, that's been a lot of fun. Now we're going to start doing it backwards. I'm going to give you the derivative of some function, and you're going to try to figure out what function I took the derivative of to get the function that I just gave you. And that brings us to this definition. We'll call a function capital F of x an antiderivative of a function lowercase f of x if, when you take the derivative of capital F of x, you get little f of x. For example, suppose I give you the function f of x equals 2x. You could probably guess that capital F of x equals x squared is an antiderivative. And how do you know? Well, it's easy to check. You just take the derivative of x squared and you get 2x. And then you come up with an interesting question. Is this the only antiderivative of the function 2x? Think about that for a moment and see if you can't come up with another. So pause the video, think about that, come up with another, or even if you can't, when you're ready, unpause the video and we'll do it together. And it turns out that there are lots of others. Take capital F of x to be x squared plus 17, or x squared plus 92, or x squared plus any constant. And the derivative of any of those is still 2x because the derivative of a constant is 0. Which brings us to this important theorem. If we have any antiderivative capital F of x of some function f, then every antiderivative looks like that function, capital F of x, plus some constant. In other words, all the antiderivatives simply differ from each other by a constant. And how do we know that? Actually, we proved this as a corollary to the mean value theorem. We said that if two functions have the same derivative, then they differ by a constant. And if two functions have the same derivative, that's saying that they are both antiderivatives of the same function. Looking again at our example, f of x is equal to 2x. Capital F of x equals x squared plus c, where c is any arbitrary real number, is what's called the general form of the antiderivative of the function 2x. Okay, we need some notation. Certainly, whether you use an upper or lowercase letter can't really be what distinguishes a derivative from an antiderivative or a function from its antiderivative. And going out of, saying the whole x squared plus c is the general form of the antiderivative of the function 2x, that's way too much. So we need something a little bit more concise and mathematical. And here it is. If capital F is an antiderivative of the function lowercase f, then we write it like this. This we read as the integral of f of x dx is equal to f of x, capital F of x plus c, or the integral of f of x with respect to x is even better, is equal to capital F of x plus a constant. And when we're talking about the integral, we're talking about the general form of the integral. This is often known as the indefinite integral. Later on, we'll talk about definite integrals. And notice that it's an infinite family of functions. Whatever the function capital F of x is, plus any possible real number as the constant c. And so the general form of the antiderivative, or the indefinite integral of some function, is an infinite family of functions. And so in the context of the example that we've been looking at, we have that the integral of 2x with respect to x is equal to x squared plus c. Very easy to check. Take the derivative of x squared plus c, and you get 2x. That's how you know that you got this right. And now we're in this situation where we have all these rules for taking derivatives. Well, turn them around and they give us rules for finding integrals. Just to give one quick example, we know that the derivative of the secant of x is the secant of x times the tangent of x. And that means that the integral of the secant of x times the tangent of x with respect to x is just the secant of x plus a constant. Okay, you try these two, and at this point, the only method you have for trying them is guessing. So guess, check your answer by taking its derivative and see how well you did. And if you didn't quite get it, modify your guess and see if you can't zero in on the antiderivative here. So take a few minutes, pause the video, And when you're ready, start it back up again, and we'll see how you did. For the first one, the sine of x, well, the derivative of the cosine of x is the negative sine of x, so that doesn't quite get us there. But if you take the derivative of the negative cosine of x, then you get the negative sine of x, or just the sine of x, and the derivative of a constant is 0. And so the antiderivative, or the integral of the sine of x with respect to x, is the negative cosine of x plus a constant. And for the second one, you have to ask yourself, well, what would I take the derivative of to get x squared? And you probably came up with some flavor of x cubed would have to be used. But if you just used x cubed, well, the derivative of x cubed is 3x squared, not x squared. But if instead you take the derivative of 1/3 x cubed, well, the derivative of 1/3 x cubed is x squared. And again, the derivative of the constant is 0. And so the integral of x squared dx is 1/3 x cubed plus a constant. And that last example is so important because we are often taking the antiderivatives or the integrals of various powers of x. And so it would be great to come up with a rule for the integral of x to the n in general, so we didn't have to just think about it. And I claim that the integral of x to the n with respect to x is x to the n plus 1 divided by n plus 1 plus a constant, or if you prefer, 1 over n plus 1 times x to the n plus 1 plus a constant. Very easy to check. Take the derivative, you bring down the exponent, and n plus 1 over n plus 1 is 1, and you get x to the n plus 1 minus 1, which is just n, and so you get x to the n, and so this works. But you do have to worry about it ever so slightly. Does it work for all possible values of n? Take a moment and see if you can come up with a value of n that it does not work for. And maybe you thought of it, I didn't give you much time and I didn't even ask you to pause the video, but it doesn't work when n is equal to -1. How come? Well, you'd be dividing by 0. -1 plus 1 is 0. You can't have that in the denominator. And so as long as n is not -1, you can apply this rule. On the other hand, what if n is equal to -1? What's the integral of x to the -1 with respect to x? Or the integral of 1 over x dx? Same thing. And you're probably thinking natural log of x because you know that the derivative of the natural log of x is 1 over x. That almost works. The problem with it is the natural log of x has a domain of only positive numbers. And at some point in this class, we went through the trouble of determining that the derivative of the natural log of the absolute value of x is also 1 over x. And this has a domain of all real numbers except 0. And so is the better function in many senses. And that's why we say that the integral of 1 over x with respect to x is the natural log of the absolute value of x plus a constant. You can think of it this way: the natural log of x without the absolute values is just a special case of the function natural log of absolute value of x, the special case that only works for x values greater than 0. We may as well take the largest function, the function with the largest possible domain, whose derivative is 1 over x. Okay, try these just for entertainment. They shouldn't be too hard. Take a little time, pause the video, and when you're ready, start it back up. You get that the integral of e to the x dx is just e to the x plus a constant. Everybody's favorite function in calculus, the derivative of e to the x is e to the x, and the integral of e to the x is e to the x. So it's beautiful in both directions. The integral of the secant squared x with respect to x is the tangent of x plus a constant because the derivative of the tangent of x is the secant squared x. And hopefully you remembered this last one. It does show up quite a bit. The integral of 1 over 1 plus x squared dx is the arctangent of x plus a constant, once again because the derivative of the arctangent of x is 1 over 1 plus x squared. Okay, try these two. Do it by guessing what you would take the derivative of to get these two functions. Pause the video. When you're ready, start it again. The integral of 6 times the cosine of x dx is 6 times the sine of x plus a constant because the derivative of 6 times the sine of x is 6 times the cosine of x. And similarly, the integral of 7e to the x dx is 7e to the x plus a constant. For the same reason, the derivative of 7e to the x is just 7e to the x. And here's what's going on here. The integral of a constant times a function is just the constant times the integral of the function. In other words, you can pull the constant outside of the integral, just like you could pull the constant outside of the derivative, just like you could pull the constant outside of a limit. All right, now try this one. And the reason I'm having you sort of play these guessing games is so that we can come up with rules like the one that we just did a moment ago. But for now, see if you can find some function whose derivative is e to the x plus the cosine of x plus x cubed. So pause the video for a moment, and when you're ready, we will move on. And hopefully you came up with e to the x plus sine of x plus 1/4 x to the 4th plus a constant. If you take the derivative of this function, you get e to the x plus the cosine of x plus x cubed. Don't forget that arbitrary constant at the end. It's very important. It gets more and more important the further along we go. So get in the good habit of remembering it right from the beginning. And this last example illustrates this principle that the integral of the sum of two functions is just the sum of the integrals of the functions, meaning if you have these functions that you're adding together inside an integral, you can just integrate each one separately and then add the results. And now the fun begins. I'll go through this example very slowly. In the future, you'll be able to do this pretty much in one step, just like we did when we were taking derivatives of polynomials. I went through the first example very slowly and carefully, step by step. And now you take derivatives of polynomials pretty much in one shot. By the rule that we just came up with, we can take this integral that we started with and break it up into a bunch of integrals, the integral of the first term plus the integral of the second term plus the integral of the third term, etc. And then by the principle that we came up before that, we can pull the constants outside of the integrals. And then finally, we know how to integrate x to the n. And so, for example, x to the 9th, you add 1 to the exponent, that gives you x to the 10th, and you divide by what you come up with. So you divide by 10, so 1/10 x to the 10th. Similarly, the integral of x to the 4th, 1/5 x to the 5th, etc. You can think of this part here as x to the 1st, and that's why when you add 1, you get x squared, and then you're dividing by 2. That's where the 1/2 comes from. And if you really wanted to, you could think about this part as 2 times x to the 0. And when you add 1 to x to the 0, you get x to the 1st, and that's our 2x right here. You can think of it as dividing by the 1 that you come up with as well, 2/1 times x to the 1st. Or you can just think of it as the derivative of 2x is 2, and that's why the antiderivative of 2 is 2x. And then all that's left is to simplify the constants, and then we're done. Okay, you try these, pause the video. It should take you just a little bit of time. And when you're ready, start the video back up, and we can check your work. Okay, the first one was probably not too bad, and you probably did it in just one step. The only complication might have been if you couldn't read my horrible writing that said x to the cube, x cubed as the second term. So if you got that one wrong, I'll count that as my fault. The second one is trickier. Before you can actually do the calculus, you have to do a little bit of algebra. In particular, you'd like that to be 5 times x to some power, because we have a rule for how to take the antiderivative of x to any power other than -1. And the square root of x is x to the 1/2, so this is the integral of 5x to the 1/2 with respect to x. And when you add 1 to 1/2, you get 3/2, so we get 5 times x to the 3/2 divided by 3/2. And dividing by 3/2, the same thing as multiplying by 2/3, so that in the end we get 10/3 x to the 3/2 plus a constant. And you're perfectly welcome to leave it as 10/3 x to the 3/2 plus a constant, but you should be comfortable going back and forth between rational exponents and radicals. It's the same thing as 10/3 times the square root of x cubed plus a constant. Same idea for this third one. Before you can do the calculus, you have to do some algebra. You need to rewrite 8 over x to the 5th as 8 times x to some power. And 8 over x to the fifth is 8x to the negative 5. Now we're ready to apply our rule. And you have to be a little bit careful. When you add 1 to negative 5, you get negative 4, not negative 6, a common mistake. And so we have x to the negative 4 divided by negative 4. And so after you simplify, this is negative 2 x to the negative 4 plus a constant, or if you prefer, negative 2 over x to the fourth plus a constant. It's the same thing. And finally, the last one. Don't be tempted to take the integral of x squared and multiply it by the integral of x plus 1. We have said nothing that would imply that that works. It does not work. And if you did try something like that, then you could take a look at the answer that you came up with, take its derivative, and see if you get x squared times x plus 1. You will not. And so the trick here, like in so many other cases, is to do a little algebra first. The algebra is easy, and if you do the algebra first, then it makes the calculus easy. In particular, if you distribute x squared times x plus 1 is equal to x cubed plus x squared, and the integral of x cubed plus x squared is not difficult, we get 1/4 x to the fourth plus 1/3 x cubed plus a constant. Okay, I want to show you one more thing before we call it a day. Let's look at this example. Suppose we have some function whose derivative is x squared plus 3e to the x, and we know that when we plug in 0 to the function, we get 10. What is the function? Well, the idea that the derivative of the function is x squared plus 3e to the x means that the function is an antiderivative of x squared plus 3e to the x. And at this point, that's probably not difficult for us to do. The integral of x squared plus 3e to the x with respect to x is just 1/3 x cubed plus 3e to the x plus a constant. But this is the general solution to the antiderivative or to the indefinite integral. This is an infinite family of solutions. We're being asked for the particular solution that also has the property that f of 0 is equal to 10. And so how would you find the particular function that has that property? Well, you'd plug in x equals 0, set the result to 10, and figure out what c has to be to make that true. In other words, plugging in x equals 0, we have 1/3 times 0 cubed plus 3 times e to the 0 plus c, and we know that that's supposed to be equal to 10. And since 0 cubed is 0 and e to the 0 is 1, that tells us that 3 plus c is equal to 10, or c is equal to 7. In other words, the function f of x equals 1/3 x cubed plus 3e to the x plus 7 is the only antiderivative of x squared plus 3e to the x that also satisfies the condition f of 0 equals 10. Okay, you try this one. For some function f, its derivative is 1 plus the sine of x, and f of pi is equal to 1. Find the function f. Take a moment, pause the video. When you're ready, start it back up. Since the derivative of f is 1 plus the sine of x, f is the antiderivative of 1 plus the sine of x. And that's not hard to compute. It's x minus the cosine of x plus c. We can check. Take the derivative of x, you get 1. Take the derivative of the negative cosine of x, and you get the positive sine of x. So we're in good shape there. And the derivative of the constant is 0. And we're told that f of pi is equal to 1, which means that pi minus the cosine of pi plus c is equal to 1. And all that's left is to solve for c. And since the cosine of pi is negative 1, we get pi plus 1 plus c equals 1, or c is equal to negative pi. And so the function that we're looking for is this one here, f of x equals x minus the cosine of x minus pi. Okay, just a couple of quick warnings about notation so that you're not confused when you see your homework. Something like this, the integral of 1 over x squared dx, is often written in a sort of abbreviated form like this as the integral of dx over x squared. They mean the same thing. You can think of it all as multiplication. Dx in the numerator is the same thing as 1 over x squared times dx not in the numerator. So they're the same thing. You would do them both the same way. You'd write this as integral of x to the negative 2 dx and then just apply the usual rule. The other thing that you might see that some people find confusing is something like this, the integral of dx. And if it helps to think about it, you can write that as the integral of 1 times dx. Certainly 1 times dx and dx have to be the same thing. And the idea is, well, what do you take the derivative of to get 1? And this is just x plus a constant, because the derivative of x is 1. Okay, there'll be lots of practice on your homework. I realize that it's confusing to suddenly be going backwards, but that's why there's lots of practice. So have some fun with the homework, and I look forward to seeing you in class. Bye.